In this video, we're going to think carefully about one idea, second-order partial derivatives. By the end, I hope this idea feels simpler and more connected. Second-order partial derivatives describe how slopes change. So they are about curvature, not direction. Now, it is really important to keep that in mind during the entire video. So it's about curvature. As you may know, in single variable calculus, we have learned first and second derivative, or like first and second derivative test. For first derivative, it's about slope. So we are interested in finding a slope in a point in 2 dimensions, while second derivatives find the rate of change of the slope. So it's about concavity. In the same sense, in multivariable calculus, first order partial derivatives, they measure the slope in one direction, right? In x direction or y direction. While second derivatives are about how the slopes in one direction changes. For first order partial derivatives, together they define the tangent plane. In other words, they describe the best linear approximation. And second order partial derivatives describe how the linear approximation itself changes. So it's about, I would say, rate of change of rate of change. Now let's talk about them mathematically. Basically, there are 4 different second-order partial derivatives. First 2, they are second-order partials, which measure curvature along coordinate directions. What I mean is that, for example, second-order partial x, it measures how x slope changes as x changes, while partial y measures how y slope changes as y changes. So they measure how the slope changes as the same direction coordinate changes. While the last 2 are called what is called mixed partials. People often get a bit confused when it comes to mixed partials, but it's not that complicated. It's actually kind of simple. Mixed partials, they measure curvature, how curvature in one direction affects curvature in the other. So it's about surface tilts. So this first 2, these are the mixed partials along the same coordinate direction, right? So they tell us whether the surface is bending or downward in each direction. While the last 2, these capture how surface tilts. That's all. All right, we are almost there. Lastly, I wanted to talk about one theorem. It's called Clairaut's theorem. By the way, before talking about the theorem, I just wanted to say in this video we're not going to cover about like how to actually find second-order derivatives in a real problem. Just briefly speaking, when you want to find second-order partials like derivatives, for example, for partial x, you just need to find the derivative of x value while treating y constant. When you want to find mixed partial y, you just need to find the derivative of y while treating x constant. So it's really simple. But I just wanted to keep this video for a more like an interpretation and deep understanding. Now let's get into the Clairaut's theorem. So it says if the mixed partials are continuous near a point, let's say like AB, then the mixed partials are equal. It sounds pretty interesting, right? It is actually. So what it means is that when a surface, let's say there's a surface in 3 dimensions, and there's a surface like this, I don't know, something like that. It's not well drawn, but let's say there's the surface is so like smooth enough, then the order in which we measure curvature doesn't matter. That's what this theorem is talking about. One important thing to keep that in mind is that this theorem is not about the definition of differentiability. It is just a consequence of smoothness. So the fact that the existence and continuity of mixed partial do not guarantee that first-order partials behave well enough. Because mixed partials are about how slope changes, but differentiability is about whether derivative fit together like coherently, so it defines a tangent plane. So differentiability is about first-order derivatives, like partial derivatives, because they are linear behavior, while mixed partials, like second-order mixed partials, are just about how slope changes, more specifically how surface tilts. Today we explored second-order partial derivatives. Now we understand curvature. Next time, we're going to talk about the tangent plane, which is the most important linear approximation in multivariable calculus. I think we are ready to talk about it because we now know what first-order partials and second-order partials are. It's going to be very interesting, so let's keep things simply connected until then. Thank you.